some text, and now we have 15 minutes to start on a subject for which there's a whole course, which is the MapReduce class. Okay, so but since we have all this knowledge, hopefully we can do a lot of it today. Okay, so let's go and remember where we came. We started off with saying that we want high performance, and we might have a non-distributed existing single thread program, and we might go and use OpenMP to make it a non-distributed multi-thread program. Okay, and I've told you all that I know today, more or less, about that subject, which is much more than what I knew 2 weeks ago, and much more than what I knew before December. Okay, so this has been a learning experience as much more for me probably than for you guys. Okay, so let's go and now take the next step. How to create a distributed program, and in the distributed program, how to create multiple threads too. Okay, and you can say that to make the transition. So there is something called distributed OpenMP. Okay, what does OpenMP require? It requires the threads to share memory, and the memory can be shared directly through hardware, or you can simulate shared memory. That every time I go and reference a particular variable that's not in my rest space, the computer, we send a message across to the computer that has it. So if I'm a slave computer, I send a message to this, I send a TCP/IP message, get the data back, and I've got remote memory access. And the first paper I read about this was published in actually 1982. So this is a very old paper. Okay, and so we can do something like this, where input comes into the master process. So this is the general OpenMP architecture. Input comes into some master process. I don't know what this vestigial master M there is. I'll delete it later if it's not relevant. So what happens? We are in a for loop, okay, or in a parallel loop. We do some splitting. In a for loop, we do iteration splitting. That goes to some threads that do partial reduction. Okay, we are really looking at reduction here. Okay, these guys. So this is the non-distributed model. In the distributed model, we might fork off a new process with its own thread and give the work to a thread there too, and assume that we have distributed shared memory, where that thread just goes and sends messages to access shared memory in this place, and we've got distributed computing, right? So now these guys do there's partial local reduction, there's partial remote reduction. Remote being in a different process. The data go back to the master. Master now becomes a master and reducer because it does the final reduction and writes to the output. That's the model. Okay, this is distributed. This is not MapReduce. Okay, but it's distributed, and it follows directly from OpenMP. Now, why don't we want to go for this model? Why bother going with something else? Whatever MapReduce is, why do we need that, given that we could do something like this?
Wait, is the question, why do we want this, or why do we not want it?
Why is this not sufficient? In some cases, it may be fine. But when you think of distributed computing, big data, that's a hint. Yeah.
Okay, well, the big data hint just threw off my answer. But I was going to say maybe because there's a lot of overhead maybe in doing partial remote reduction, just tossing that over there. Maybe could have been done locally. Depends on unless.
Okay. So this is an option.
Yeah.
We don't have to use it. The assumption is that somehow the number of I don't have enough processors. Gati's job is running on my computer. So I want to go to another computer. Okay. So where is the overhead? Once the other computer starts computing, there's no problem, there's no communication. So where was the overhead?
On the network, on the wire.
Sending the data across and getting the data back. Yeah.
You need some sort of heartbeats to keep track of all your slaves.
So you need all that overhead, okay? Which we kind of gonna need in distributed computing anyway. So I'm saying, we're going to go to a different model, which you're the expert on, so I'm going to defer to you a lot. You're taking that course. So anyway.
That course is surprisingly short.
Oh, shh.
Just total stuff.
Okay. Yeah. So what do you guys think? Big data. I have billions of records.
I'm just gonna say it, but I don't know. I mean, your inputs can be from many different places. So that,
Came in different places, but everything is coming into this master process has got, if it's got billions of data, this particular master process has got to go and put it in its memory, the whole data. That's one problem. Then farm out to everybody else. Because that's how OpenMP works. OpenMP says we reached a for loop. This is what the data, it doesn't know about data structure. It says you've reached a for loop, you've got some variables initialized. Now we'll go and make sure that we'll create local copies of these variables, we'll do splitting. It's all memory-based model. So there's an overhead here. There's a bottleneck.
Is the bottleneck on the input or the output?
Both. Both.
the master has to do everything.
Has to go and split off. It has to get the work and split off. Wouldn't it be nice if people just picked up the work?
That's what I asked about that. What if the master did not pull the data in itself, but told each
So we need a different model. And you know, OpenMP, I've kind of derived by asking the right questions. I'm trying to derive now a MapReduce. Rather than just saying, here's an API, here's how it works. I'm trying to derive that from first principles. And if I can derive it from first principles from asking questions, there's something right about it and worth teaching in the class, rather than just another API. Live with it because that's what exists. So I'm just saying there's something fundamentally correct about it. Okay? And I'm going towards that. Okay? So what do we want? So guys, you want to think about what the solutions might be?
What about what I said?
By the way, I have to remember to remove that extra M circle. so yeah.
I mean, we can distribute the data before the input and then just wherever it is, tell that computer, hey.
So we have multiple masters. We just break up our data into files and use the file system to distribute things. And we have maybe multiple masters. Okay. The other problem with OpenMP is, but that is one problem. But still, we still can't use an OpenMP for loop, right? Because the for loop is based on some global variables. Okay. So for loop is not based on any data structure, even though we have always used some data structure with the for loop. We've gone through an array, we've gone through a map, we've gone through something. So maybe we don't want a loop-based or a scope-based breaking up of data. And we want basically a data-based parallelism than a loop-based parallelism. We want splitting of the data, and we want parallelism based on some data structure rather than scope of a loop. Because if you're going to depend on the scope of a loop, then we have to enter a particular application and go and create threads from that application. So we have to sort of assume that the parallelism that we have is based on separating input files, and input files, input output have some correlation with the data structure rather than a loop. Okay? So our parallelism has to be associated with the data structure, and MapReduce tells you what data structure is it associated with? A hash map. Okay, so that's the basic idea. That we're going to base a parallelism on a data structure rather than on a loop or a statement, and that data structure is going to have some existence outside in input, and we can go and distribute that input, and then the data structure is going to be written in the output. And we can have multiple threads create different parts, independent parts of the output, so that we don't ever have a bottleneck. So the output is now going to be a set of outputs. It's got to be a set, okay, created independently by different processes. So we never sort of put data in and take data out from one process, all the data in and out, all the data out.
So how do you combine that at the end, though?
It's a set.
You just...
So we just think of it as a set. So just imagine they're all writing to a file, and we know they're independent sets, so we can just make that set together into one output. And they can be, yeah. Okay. So the fork join model requires input of data to start and end at the for of one process thread. So we need a software implementation of shared memory, which we don't, which is another issue. Current systems don't provide that. Inconsistent with big data, where all data cannot fit in the memory of one process. And even if it does, that process becomes a bottleneck. Okay. MapReduce provides a comparator for fork join loop-based reduction. Okay, so no section. It's basically for loop-based reduction, not for sections and parallel constructs, but loop-based reduction. Yeah.
So you still can't avoid it entirely. At least, just focusing directly on at least MapReduce model, where between the mapping and reducing steps, you still get a whole bunch of transactions. And that's what I'm talking about. I don't actually know how that works.
Okay, we'll see how it works. Okay, but just be careful.
So each master gather a set of input-output from its corresponding.
See, you guys are deriving it. There's something right about it. Okay. So let's look at this problem we did earlier with map-based reduction. Okay. We said, if you want to do MAPPLUS A1, A2, A3, A4, we can do MAPPLUS A1, A2 into A1, MAPPLUS A3, A4 into A2, and then we can combine this, right? This step, we normally didn't consider any concurrency here. We said, come on, if there are 8 threads, what's up? There's not that many results. There's 8 pieces of data that have to be collected together because we're creating a sum, or we are creating a product. Okay. But the truth is that in this particular job, we are creating a data structure at the end, not an atomic value. That data structure can be very, very, very big. Okay. So what if I go and model it as this way? That I created really a MapPlus of 2 hash tables, each of which I can break up into key value pairs. Okay. And I'm trying to add up two hash tables that each of which can be broken into corresponding key pairs. Now, can you see some parallelism that we can do here? Assuming this particular data structure is billions and billions of records. How are we going to add up two hash maps? What does that really mean?
You could just save to the same value twice. Maybe.
No. What does it mean to add up? Remember the word count application we did?
Yeah.
So what does it mean to add 2 hash tables?
You have to insert all the elements into one hash table again.
Okay, so what happens if the 2 hash tables have disjoint keys, then the new hash table will have the set of both keys and the associated values, right? What if they have overlapping keys? In the word count, what happened? You did some function on the set of keys, values associated with a particular key. And in word count, that function happened to be an addition function. But each key can be processed separately, right? That means maybe we can go and redo this question. So further parallelism when the collection is large, I can do MapPlus K1 V1 K2 V2 K1 into MapPlus K1 V1 K1 V3 MapPlus K2 V2 K2 V4. We are assuming that adding up the values associated with the different keys is independent operation. That's yet another, just like if you take 2 sequences and you add them up, you can assume that addition means that you add the first value to the value at the first index to the value at the first index of the other collection. There are some corresponding values, and adding up elements of the first position is independent of adding up elements of the second position. We're going to make this assumption. This is going to be fundamental to our MapReduce. Okay? So you see what I've done? Now these 2 steps can be done in parallel. And finally, I can just go and just output these things because these are sets in any order. And that can be done in sort of a directory, if you will. And each guy can produce a separate file, and those files can together be merged, through some tool. into a single file if necessary, or actually MapReduce creates multiple output files. Okay? So that's a key idea. Assume data fits in set of input files other than single process. Work split to different processes by giving them different portions of files without first loading them into one process. Okay. Database division rather than loop-based division. Okay. And work combined by multiple processes that write to output files rather than sending them to one process. Okay. So there's an external data structure, file text lines, and the in-memory data structure. I'll just take 3 more minutes, and I have, I guess. The in-memory data structure is a map. It's not a bean. It's not an array. It's not an array list. It's a map. Why map and why not the other data structures? Assuming we're going to choose only one data structure. You can say, let's go and support all of them. Assuming we're going to use only one data structure, why a map and why not an array list? A bean doesn't make sense, right? Bean is going to have few number of properties. So we're not going to have large beans. Collections are the ones that can be very big. So which is more general? An array or an array list? Which can simulate the other?
Array list simulates array.
Array list simulates array. Which is more general, an array list or a map? Why?
Not that simulate arrays. It's just you have a chaining. Arrays just chain.
Well, map, that chaining is not visible to you. The keys are visible to you. So, but we can have integer keys. We can have a key be 1, 2, 3, 4, 5, 6. And then we can create the output and then sort it based on the keys. Assume we have such a sorting function. We can simulate. So, way back, there was a language called Snowball, which had only got, which is sort of like what Perl developed from actually, which had only primitive types and a table, a map. And then came a language called EZ, which said, you take these atomic values, you take a table and make it persistent, and you have all the data structures you ever need in an operating system or programming language. A directory is just a table with nested tables in it. So this map data structure has been through the ages considered a very powerful data structure. Okay, so why not map and not bean array list size? Can simulate bean in any collection array list set. Okay, you can simulate a set. In fact, sets are implemented as maps. Okay, and values associated with the same key can be reduced independently and thus in parallel. Okay, these are the key ideas, guys, and we should take, I think, I've got only 20 slides left, I think, okay, or maybe 25, 30 slides left, but it should take only 15 minutes, who knows, okay. We'll go and look at some problem sets also in MapReduce so that we really understand it, and that might take time based on how long you guys derive it. But you see the general principles here. Okay, we'll see the execution next time. Okay, we introduced MapReduce, and the idea was to go and we saw the word reduce in OpenMP, so I wanted to relate this work to what OpenMP does and explain it as a diff from OpenMP rather than something from scratch. Right? And let me just remind you how we compared OpenMP for-based reduction and MapReduce reduction. So this is OpenMP style reduction. The difference is that firstly, we are not going to be iterator based. We're not going to be based on a for loop. We're going to be based on a data structure. Okay, and the data structure we are going to choose is a map. And we saw how we can do map additions in OpenMP. We just had to go and tell OpenMP what the MAPPLUS operation was, and OpenMP just ran its for loop and did the reduction for us. Okay, so we are going to commit ourselves to the map data structure. And we talked last time about how the map data structure is a very general data structure. In fact, if you think of a relational database, that is really a map. It's a table with lots of columns, and in MapReduce, the key and the value can be just any object. Okay, so it can be an object with multiple components in it. Okay, so if we have to go and add up 4 tables in OpenMP, we will reduce the problem to adding maybe a fewer number of tables in each step. So maybe we'll create 2 threads, one that adds up the first 2 tables, another thread that adds up the next 2 tables. Okay? And then we'll go and take the results of those 2 tables and do another reduction, which goes and adds them up. Okay? And since we don't have that many threads, normally we do that sequentially. Okay? And we get the final result later. So we do the division here based on some enumeration. Since we're doing data structure based rather than loop based, we'll have to have some way of enumerating the elements of this collection map. So we assume there's a way of enumerating it, and then we can go and have the chunk sizes. And we do the partial reduction here, the final reduction here. And the question then becomes, how can you create more parallelism? MapReduce, the OpenMP is data structure agnostic. You can use it to compute the sum of a bunch of integers, or you can use it to create sum of a bunch of tables. It doesn't care whether it's an integer, a table, or whether you're computing a sum. It's just saying, let's go and divide the iterations among these threads. But since we have a map data structure, which is a collection, and this collection can get very, very large, do you guys remember how we decided to further parallelize, assuming that we have a large collection?
Something to do with keeping them as the files.
So the keeping them as files allowed us to make sure that all data did not originate at a particular process. So we had another problem with OpenMP, that everything had to be funneled through a process. It is, and then it had to go to another distributed threads or distributed processes, but it was all concentrated. So we decided that we'll go and split the data into files in a distributed file system, and those files can be at the same location, can be at different locations. So that's how we address that problem, and that's the problem that this picture is not addressing. So the idea is that how can I go and do further parallelism, given that this data structure consists of a bunch of elements, and that bunch can be a very large bunch. Yeah.
I'll take a guess. Could you do something where if a key has multiple values behind it, you send them in groupings of that value of the key?
So then what you would do is you would go and send for a key all the values. So how does that create more parallelism?
I don't know, you're just sending more to each thread to do, maybe. I'm not sure. I can tell.
You're there. You got the right answer. You just don't have the right reason.
I'm not sure.
So I'm trying to add 2 maps. How do we add 2 maps, by the way? What does it mean to add 2 maps? So supposing the first map, so let's go down here and look at this.
Just putting them almost on top of each other, like tallying like the same keys on top of each other. So if you have 2 of key A, for example, and 2 of key A in another map, it's 4 key A.
So if I have in one map some value associated with the key, in another map I have another value associated with the key, then I create a new map in which that key has got the sum of the values, right? Or some computation of the values, right? And so this picture kind of shows you, it's decomposing the map into something structured, okay? So it's saying, I'm doing a MAPPLUS on 2 maps, and I've got curly braces to delineate the maps. One of them is K1V1, the other is K2V2, the other is K1V3 and K2V4, okay? So that's what we're doing, and our MAPPLUS operation, we could have our MAPPLUS operation do anything we want it to do, but the one we wrote for parallel OpenMP was that we just went and added up the values. So we go and say, this guy then adds this up. It doesn't have much to do. And this one then goes and sums up the keys and the values it gets, so that K1 is associated with V1 plus V3 and K2 is associated with V2 plus V4. Okay? So that's what a map operation is. Okay? That we are basically summing up the values associated with the same key. So summing up the values associated with one key, is that independent of summing up the values with another key?
Yes.
Yes. So can you now tell me how to go and do this in parallel? Is summing up the values associated with key K1 independent of summing up the values associated with K2?
So you just
Right.
split it based on keys.
So you split it based on keys. Okay. So so this is interesting. I'm splitting here based on some iteration of the keys, right, in each table. Now I'm going to split them based on the content of the keys. I'm going to make my algorithm even more map specific. That's, no pun intended, but that's the key to this whole thing, okay? So we're making a big assumption that when we go and do a computation in two maps, the computation associated with different keys are independent. They needn't be. Okay, who knows what our function we want? But we have to go and make sure that the computations associated with different keys are different, are independent. They can be the same computation but independent. Okay, so this is what I'm doing. So I'm now not doing a MAPPLUS. I'm doing a sequence. Sorry, that should have been sequence plus. Okay, not plus plus. I'm doing a sequence plus where I'm getting key value pairs in a sequence where the keys could be repeated. Okay, so that's why it's a sequence. And I'm now dividing this into two sequences, into multiple sequences based on the keys. So this guy got all the key value pairs with K1. The other one got all the key value pairs also with K2. Okay, these works can go in parallel. Okay, and we can have lots of keys. So we have lots of parallelism possible here. So we can have K1 and K2 mapped to one particular reducer. We can have K3 and K4 mapped to another reducer. So there's a way of partitioning it based on keys. Okay, we can have a separate reducer for each key if we want to, or we can have multiple keys bound to a particular reducer. And then this operation, I'm calling independent MAPPLUS. It just gets all these maps that are independent of each other and just collects them together. Okay, the keys are not overlapping in these maps. So these can be outputs to different files, and we can just then say, here's a collection of files, and we can sort them and do whatever we want to with the output. Okay, so that is the main idea in how the reduction occurs, is different. We are making use of the fact that we are reducing a structured object rather than an arbitrary object. In fact, we are making sure that we are reducing a map. Okay? Questions? Okay. So can ask different processes to partition or split the input sequence among key-based reducers. So these are key-based. So we are now doing key value sequences rather than maps. And it's a simple combination. Okay. So let's go and see the architecture here. Here's some input. The input is not starting out from a particular process. It's outside. In fact, it can be divided into multiple input files, which are at different locations in this distributed file system. So I'm just clubbing them all into one input. And we do first we do inter-process input splitting. Okay. And we can do that based on load balancing, that we can make sure that the processes get right load, or we can do it based on. So I can just make sure that half the input goes to one process, half the input goes to another process. But this is a distributed file system. So can we use some other criteria for deciding which process gets which?
How close it is in memory.
How close it is in memory or how close it is in location. This is a distributed file system.
So you just don't have the page fault.
Page fault. So it hasn't even gone to the memory right now. It's outside memory.
Is it outside?
This is a file right now.
Okay, if it's a file, then you know.
So what can you're kind of there. We can split the files based on load balancing, that we can say half the file goes to one process, half the file goes to another process. But this is a distributed file system. What other criteria can I use?
What's on your local memory?
So we can start a process near the file. Okay. So if half the files are if 1/3 of the files are in Duke and 1/3 of the files are here. We start this process, the Duke process with its files, and the UNC process with its files. Okay? So people talk about in MapReduce, processes go to the data rather than data going to the process. Okay? So we can, and this kind of locality we can use. If they're both at the same location, then we can do some load balancing. Okay? Or if the UNC data is more than the Duke data, then we can start two processes on the UNC nodes, and we can start one process on the Duke node. Okay? If they're all in one data center, it's not going to make much sense. But I've seen when I read this up, they make a big deal about the processes going to data. And processes going to data make sense only when the data are kind of spread out. Okay, that you have some logical file system that's distributed among geographically dispersed nodes. Okay, at least this architecture allows that. Whether the implementation allows that or not, that's another thing. Okay, so processes go to data, that's one criteria, and or we do load balancing. Okay, so we send them first to, we have two kinds of processes that we're going to have. So the first set are the mapper processes. Okay, so now within a process, can we split it further into parallel streams, into threads, right? We've seen a lot of that in OpenMP. Okay, and here we'll do, so we have both inter-process splitting and intra-process splitting. Okay, so let's say we have two master threads that we start, map threads we start. Okay, what's the next step after mapping? So mapping, what does map do? Map takes inputs, which is a stream of input, lines and associated with line numbers associated with lines. Okay, and creates key values out of that, out of these lines. Okay, so once we've done the key values, what's the next step in the previous picture we saw? Split them based on, okay. So what we're going to do is, so we do the mapping to key values. Now the question is, the split values have to be reduced, right? Should they be reduced locally or remotely, and or both?
Isn't it dependent on the sort of how your system is?
No, we have to design the system. We are God here. We decide what happens.
But I mean, if the systems are far away.
What system? This is the process. One process. We are within the process.
If it's within a process, then do it locally.
And remember, there is distribution here. So you want to. So firstly, is the remote reduction optional step? No. Because?
That's the point.
Sorry?
Okay, that's the whole point, right? It's reducing.
It's reducing it.
Done yet when it goes to the mapper.
Right. So it goes to the mapper. It's not done yet. But can the reduction be done entirely locally, or does some reduction have to happen remotely? Yeah.
Yes, because they are on different files, like remote file systems, so different file systems. So eventually you have to combine maps on different.
You could have some keys generated here, some keys generated there. So those keys have to be combined by a reducer that's external to both of these processes. So there has to be some step done remotely. What about the local reduction step? Is that optional? Yeah.
I'm going to say no again.
Why?
Because right now it just has the chunk of the map to work.
Which is converted into key value pairs.
Yeah. It's not key value pairs yet.
No, mapping process will convert that into key value pairs.
Oh, okay.
So that's the mapping function. The partial reduction we decided has to be done remotely. At least some of it has to be done remotely.
Oh yeah, sorry, I meant in the top one. The
So,
top is mapper too, right?
Sorry?
The top and the bottom items there, processes, they're both mappers.
They're both mappers, and I've got this partial reduction step in. I've blown up the top one. I haven't blown up the bottom one because it didn't have space. Okay? So, but this process is called mapper. But this process is going to send the data to reducers, remote reducers. We know, in Tegan said that we do need those. Can we do some partial reduction within the mapper process? Not in the mapping thread, but in a partial reduction thread. And, and can we or should we? And must we? Yeah.
I think probably we should do the local reduction so that we get it so that each key is like, there's only one key in the map, and then kind of do what we did before and send each key to a different process. That way you're not having to talk to each process if they're independent and then they all come back together.
So you're saying we can do some local processing where multiple keys from the mappers can be combined into one key with the value here.
Yeah.
And then we send it to the remote reducers, which we do need to send.
Yeah.
And is this step optional? If we don't do this step, will our system still work?
Yeah.
Because the remote guy is going to do it. So this is an optional step in MapReduce. Okay? So there is some, and this process of splitting is called shuffling also. Okay? So we are now shuffling the keys, and we're going to make these reducers also key-based. Okay, we're going to do these reducers in parallel. So, some keys go to this reducer from the two different map threads, and some keys go to this reducer from the two different map threads. Okay? And we've done partial key-based reduction. Okay? And so this is called the mapper process, but this is really mapper and optionally partial reduction process. Mapping and optional partial reduction. It does both these steps. Okay? And now we need the remote reducers. Okay, and these will be the final reducers. And this is now inter-process shuffling. Okay? So some keys go to this particular process, some keys go to this process. And these are disjoint set of keys. And this is now inter-process. And now we do inter-process shuffling within the reducers. The reducers can reduce in parallel. One reducer can reduce its, the first, some keys, and another reducer can reduce different keys. So we have multiple threads here too. We don't have to, but we can. Okay, and again, these two reducers are going to work with disjoint set of keys. Okay, and then we finally do the key-based reduction, and this can be done in parallel, and we can just write it to different output files or to different parts of an output file. So this process happens outside the memory of a particular process.
Yeah. So the more work you do on the more partial you do the reduction, the less final reduction.
Yeah. The more partial reduction you do, the less final reduction you have to do. Okay, and you want to keep the work localized if possible. Okay, as long as you have the horsepower to do it. Okay, if your mapper process is a very weak machine, then you might want to leave it to the final reduction. So this is an optional step there. Yeah.
I have two questions. So this might not be important, but the output it has to be a different process or at least some different data structure that both those reducer processes are saving to.
Yeah, so we write it to a distributed file system, and the simplest way I can think of is that each reducer writes it to a separate file, and these files are together written in one directory. Okay, and I do know that they create multiple output files, and they take multiple input files as input. Okay, so we just they could write to a relational database for system, for instance. I mean, that can be anything. And database systems do allow parallel access. A lot of work has been done in that. So I'm kind of leaving that part outside. I'm just saying there's a way to write this in parallel to persistent store.
Okay, I was just curious. I mean, I assumed it had to be a separate process.
Yeah.
Couldn't be.
What is a separate process?
Well, not a separate process, but like a separate process that's taking in all the sums from reducers.
Yeah, I'm just output is just some persistent store.
Right.
Some geographically distributed file system, database system. I believe it's a file system there. But in principle, our programs will work even if you change, our reducers and mappers will work even if you change the persistent store. Okay? And you know that, when you make an airline reservation, there's a database there, and our airline reservations are processed in parallel. So there is a way to go and access them in parallel. Now, sometimes you get errors too, and that's why you get overbooking. But anyway, yeah. Andrew.
So is this correct? The mapper and the reducer pair are on one host?
That is what the circle is trying to say. One process. Yes.
So for the bottom.
These yellowish boxes are one process. Yeah, I mean, each yellow process is a process. Okay, and each of these smaller circles is a thread.
So there's 4 processes on the screen and 12 threads, basically?
Yeah, if they're,
That's how I'm seeing it.
if they're,
How do you see 12 threads?
I'm just-
Oh, if you're doubling. Yeah, who knows what the other mappers has? It could have,
Right, so each mapper is on a different host, right?
it's on a different process. As you know from your assignments, which host you put a process on is up to you. But probably. Why have 2 processes do this on the same machine? Okay. It's only when that machine is doing other tasks that you go and put as many processes as possible so that you get more work done, for your task. Yeah.
Why wouldn't you do local reduction? Is there a scenario where it's better not to?
Maybe the reduction is an identity function, which just takes the value and outputs it. We'll see a problem that involves that. So why even create these threads if the reduction process is very minimal? We are going to compute some function of the values associated with the key. It doesn't have to be a plus. It could be a min. It could be the identity function that just goes and says, so there can be many reasons. At least those can be the reasons.
It's depending on the nature of your reduction.
Nature of your problem. Yes, nature of the mapping and the reduction. The mapping can do some computation. The mapping takes input text and converts that into key value pairs. It can do some computation there. But that computation is very localized. It's restricted to that input line. Okay, it better not depend on other input lines. Whereas the computation being done by the reducer is dependent on, is not localized. Okay, it can depend on data in different input lines that map to the same key. So they're both doing some computation, okay, and you can distribute the computation among the mappers and the reducers and between partial reduction and final reduction. But they compute the exact same function. The partial reduction and reduction is just to get different data. Okay? Questions? So let's do a problem. Now my oval boxes have got replaced by rectangular boxes because I couldn't fit things in. I tried my best in the beginning. Okay, but these are still different processes or hosts. So I have an input file, and let's say this gets split in the following way. I'm doing a word count. Okay, this is the problem we saw earlier. So I've got 2 lines on this for this process and 2 lines for this process. Okay, the first line has got 2 words in it. The other lines have got only 1 word each in it. Okay, so each input line has to go to a single mapper, but different input lines can go to different mapping threads and mapping processes. Okay, the input lines are supposed to be independent. Okay, so now let's look at the map process. This is my input. I want to find out how many the's appeared, how many A's appeared, how many ands appeared. So tell me what my mapping function is going to do. It's going to get an input line. What is it going to do with that input line?
split it,
Sorry?
split it,
Split that into words, and then do with what with each word? Do what?
use it as a key, and then give it a value.
So we have to generate key value pairs now. Okay? And we make that as the key and give it the value 1. Okay? So mapper ignores the position. It ignores 1, 2, 3, 4, it doesn't care. Okay? And it goes and converts that, and two different map threads can go and compute the first and work in the first and second line in parallel. Okay? So the first thread has gone and worked with the first word in its line, and the second guy has worked with the only word in its line. Together they did it, and this guy then goes and works on the second word in its line. Right? And something similar happens here. And what's my reducing function going to do? Given a bunch of key value pairs,
It's going to simplify this.
it's going to further reduce it and simplify and reduce the synonymous words. And what's the function exactly going to do?
So both of these would go to the same reduction process.
No. Now, reduction process or reduction thread first?
Partial reduction thread comes first, right?
Yeah. So what's going to happen? So we have to generate some thread, assuming we have. So yeah, you go to two different threads.
Okay, so both the A keys go to the same partial reduction thread. The
Yeah.
does to its own, and so on. It then goes to a reduction thread where all the does would together all the A's.
So these two A's will be partially reduced locally,
Yeah,
and this dir and that dir will be reduced
over there.
remotely, right? So dir goes here, dir goes here, A goes here, and the A goes on top of that A, so it becomes A2, okay, by one thread. I ran out of space here. So this is the result of the partial reduction local. And now all the dirs go to one place, right? And that produces dir 2. A's go here, and goes here. That creates these two results, and we get these data. Okay? The output can be done in parallel also, like I said, but you get the output.
I will ask this, maybe we covered this and I forgot, but how does one mapper process know to send to the same,
So there has to be some function that they all use, which is a partition function.
which I mean, I guess that means it has to be familiar with all the input it might get too.
So we go and how would you do, supposing you're given words, how would you decide which,
Alphabetically, the different resolutions.
maybe based on alphabetic thing. Okay, that's one way to do it. But so if you do assignment 0, which I hope which at least 2 of you have done, you can write a partition function that goes and lets you decide which way it goes. So you can control it. Okay. Yeah. Okay. So these are the kind of changes I made to the assignment 0, MapReduce assignment, that I made it more like MapReduce so that you understand the process better. Okay. Get it? That's MapReduce. But let's go and actually see some code. Okay, and I didn't write this code. I just copied and pasted from the manual. They've got this example. Word count is the canonical example they use in MapReduce. Sum is the canonical example they use in OpenMP. And it's not summing up the values in an array, it's summing up the first n numbers. Okay, because again, you want to teach this at the very early level. People don't know arrays early. They know how to sum up, values from 1 to n. So that's the kind of example they use so that it can be taught without assuming too much. Okay. So we see here that we have this map function, and it takes did I just give you guys the reduce function here? No. So it takes a key. Oh, so the long writable key is the line number. Okay, that's that. I was getting confused by that. I said, well, why is it getting a key when it's supposed to compute a key? So it's also getting a map. That map is line numbers and line contents. Okay, and it's getting the text, and if you've started, so rather than returning back a value, it gets a data structure into which it puts values. So that is the return value. Okay, so it's like saying, don't return an array. Here, don't return an array. Here's an array that I give you as an argument. Fill the array up.
It's an output.
Output parameter. Okay, and if any of you go and do the serializer assignment, that's the kind of way that's how you serialize, by the way. That there's this long serializable text you have to generate. It's the job of filling it up is distributed among multiple methods, and they all take the same sequence and fill it up at different times. Okay, so that's the thing you're doing, and you go and convert the value to toString. You break it up, just as we saw there, and then you say, okay, output.collect. You call this collect operation that goes and adds an operation, adds something to it, and it's doing word, comma 1. Okay, and look how good they are with named constants. Okay, 1 is a named constant. It's not the number 1 or not new int writable 1. Okay, so all this preaching I do for good style, these guys adhere to it, which I'm very happy. A lot of code you see on the net doesn't adhere to good style. Okay? Questions? Can we do this loop in parallel, by the way? There's a while loop here. Could I do this in parallel using OpenMP or using some variation of OpenMP?
Yeah. Because the lines are independent of each other.
The lines are independent of each other, except that OpenMP assumes that the iterations are independent of each other. So it takes the index I. Here it's doing next token. So next token is something that has side effects. Right?
What do you mean?
Oh, I guess you could just rewrite next token using I to count. Maybe.
So you could do initially, imagine doing in Java an iterator based thing where you iterate all the lines at the start, right? And then divide the iterations in elements among the loops. So you don't do has next. You're just given the next line. Okay, and someone outside is doing the has next and next token. OpenMP will not allow this right now. But you can imagine a variation of OpenMP that is associated with iterators that divides the loop iterations based on that. Okay? So I'm again trying to show you the link between OpenMP and MapReduce, and there's yet another link.
I was just going to say, I think that you run an iterator problem you're talking about, but I still don't understand why we couldn't empty the tokenizer first into a local data structure.
That's what I'm saying. That's what the iterator does. So I'm just saying we can't use this loop. We'll have to use another loop where we empty it into an array and then go and use the array index.
That'd probably not be more efficient.
And the thing is, we need to know, we still need to know which portion of the array we are getting, right? So this input data structure is maybe shared among multiple threads. We don't know whether this data structure is, created, we've got our chunk. This could be just one long iterator, and every thread is going in doing has next, and every thread gets some of these lines. So it may already have been doing some splitting.
Is that OpenMP can't do this, or OpenMP for Java can't do this?
OpenMP can't just take this particular loop and do it for any language. Okay, it'll have to be an index-based thing. But I just want you to think about that, what's really happening is that MapReduce is already figuring this out. It's created multiple threads. They're all doing has next on a common data structure, and depending on what lines one thread has got, another thread will get different set of lines. It's probably not doing a static allocation. Okay, it's probably doing a dynamic allocation. That's all under the cover. We don't know what's happening. But we can imagine all these variations based on what we learned in OpenMP. Do you have a question? Okay.
Nothing can do that particular loop in parallel because the next token tokens have to be done atomically. So if you could, the collection could be done in parallel, but other than that, everything has to be serial.
No, but the key value generation can be done parallel.
Yeah.
And this stuff can be done before the loop.
Yeah, so if you can't, I was saying, not just that OpenMP can't take that loop as is and do it, nothing.
Yeah. No, so OpenMP can't, but we can imagine what's probably happening is that this is accessing, the input string is being accessed multiple threads at the same time. Okay, and you're doing has next on the same expression atomically, but that will slow things down. It'll slow things down. But so the right way might be to just go and take chunks and divide them in the beginning, and yeah. So I'm imagining sort of doing what Chris was saying, that we just do it earlier and then just give it an extra argument, which is the line. Yeah.
So I think I understand how we would create our local data structure for this. Is there any way that we could use a multi-threading system before this to manage that the local data structure? So you give a chunk to a thread.
Yeah. So do you have any control?
Yeah.
As far as I know,
No.
as far as I know, but if there is a need, there must have been a way to do it. This is a very configurable system. I haven't even read the whole thing. I just went to Don's office one day and tried to understand it. Okay? So there's probably everything can be configured, and even the partitioner can be configured. But I believe this is based so much on runtime behavior. But all the issues we studied in OpenMP, static splitting, dynamic splitting, chunk size, all those issues come around here, and they just provide a solution to it. Okay, but we can imagine OpenMP and MapReduce working in tandem, where OpenMP gives us the flexibility we want with its parameters, and MapReduce just does the inter-process splitting. Okay, and that's why maybe one of you guys are going to design such a system. There's a few. So that's why there's a lot of future here. This is nothing set in stone here. Okay, but you can see that the decision that is taken can be motivated from first principles. Okay. So now again, what we're doing is we are parallelizing. So this is not being parallelized. Okay, I'm just talking about parallelizing. The parallelism is occurring at a method level. You just give it a method, and it calls the for loop around it, rather than like an OpenMP saying, "Give me a for loop and I'll try to understand what you're doing there." So you have to fit to the infrastructure. The infrastructure is not trying to fit to you, not trying to learn from you. And again, the idea is that you just write as you write regular programs, and then think about parallelizing them. And maybe you're taking existing programs and parallelizing them. Okay. But this is very method, and you can see how this can be mapped to different threads, right? We already got a method here, just go and make that method be executed by runnable. We don't have to do all that pre-compiling that we had to do in OpenMP, extract out the scope, copy it into the variables. This is just, So this is another way of doing parallels. Okay? And the infrastructure provides some of the types. Not only do you have to implement their interface for the map method, you have to use their types, which is kind of saying the same thing. You have to use their output collection, you have to use their input collection, and so forth. There is some flexibility in, which you can subclass their input collections into your own subclasses, okay? But the superclasses of these input and output collections are given to you, okay? So the mapper transforms input to reducible output, basically. That's its job. We have input, we have output, and it just converts one list of key value pairs to another list of key value pairs, where the keys in one case are the lines and words, and the other case it is whatever you want it to be. So that's the question we addressed, loop parallelizer by OpenMP. And here's my reduce function. And the reduce function, you don't have to go and find all the keys in the list. It says, okay, here's a key and all the values I've received for that key. So you get one key item and you get all the values associated with that thing as some kind of collection, okay, iterator. And you just go through the iterator and go and say, okay, collect whatever key argument you got, and you go and compute some function on these values. Okay. So the reducer is like an n-ary method. Okay, it's not doing it two at a time. Okay, it's just getting all the values. It has to write its own loop to do it. And again, we can imagine parallelizing this loop also. Okay. So output is set of final key value pairs. Okay, same question, same answer. So here's the interesting thing. In OpenMP, you write a problem from scratch and tell OpenMP about parallelization relevant aspects. Okay, you write your loop and then go and inform OpenMP that this is to be parallelized or not. This is my operation. Okay. Here you transform problem into a map and reduce method. Now, which do you think? This is a judgment call. Which would you prefer to use, given a choice? Transforming into some problem, or just from first principles doing the problem with fewer constraints? Second one?
I feel like I understand it more because
Sorry?
I have more control.
You have more control of the first one.
So we're choosing between OpenMP and MapReduce?
We are choosing between these two approaches.
Because I feel that MapReduce is probably something that's more understood and less buggy than OpenMP, which might have some holes in it and less than clear details in it.
OpenMP is being taught to 110 level students. How many times am I telling you that?
I get that, but it doesn't mean it's perfect.
You have to know about the reduce function, you have to know about functions, you have to know about collections. But I'm going to work at a very philosophical approach. Forget about the buggy and all that stuff. I'm totally philosophical. Do you want to transform your problem into some existing problem, or do you want to do it from scratch? And there are other analogs here.
Well, I'm going to go with the existing problem, which is converting the MapReduce thing to work with OpenMP, right?
No. In MapReduce, to go and you have a problem. You want to sum up the values, or you want to go and find the word count. Do you want to transform your problem into the OpenMP, into the MapReduce data structures, or do you want to build from scratch? That's my question. I'm not transforming OpenMP into MapReduce.
No, I'm not saying that. I'm saying making the MapReduce model work with OpenMP in the last.
No, I'm not saying that at all.
Oh.
I'm saying you're given a problem from scratch. Find the word counts. Either you can take, listen to me, okay? You can either use OpenMP to do the problem from scratch, or you can transform the problem into a MapReduce data structure. MapReduce and OpenMP are totally two independent things here I'm trying to say.
I'm going to change my mind and say from scratch.
Okay, let me, and before you, yeah.
I think like if the problem is more complicated,
So it depends on the problem.
we can reduce to the map and the reduce method. But like if the problem is simple, we can use OpenMP.
So you're saying when it's simple, use OpenMP. When it's complicated, use MapReduce. So,
I'd say if the keys are obvious, then use MapReduce.
so if the transformation is easy, then use MapReduce. Otherwise, you have more control. So maybe the complicated problem is the one that doesn't cast very well into MapReduce. Okay. Let me ask you these guys this question from your automata theory stuff. You're given a regular expression. You have to prove you have given an expression. You have to prove it's regular. I had to do this for my PhD exam, for instance. Okay. You can either create a finite state automata for it. You guys did that in your course. Or you can convert the expression into, using some transducer, into a known regular expression. Okay, you guys didn't study this. In my class, we had a professor from Stanford. I was in Madison. Professor Barwise, I remember his name. He taught us this transducer that you can convert the strings. If you can pass your regular expression through this transformer, and out comes another expression that is known to be regular, then what the input was also regular. I loved that machine of his. In my PhD exam, there was this question to prove this regular among all the things. I just wrote a transducer, 3 lines. And I asked my friends later, and they wrote 2 pages of FSA to prove that. And I asked my instructor, Udi Manber, who I mentioned earlier, he was the chief technology officer of Google or Yahoo, one of these 2 companies later. I said, did you expect my answer? He said, no, I didn't. I didn't even know about this transducer. So I might not have got my PhD if I hadn't used that. So it depends if the conversion is easy. And you guys studied the halting problem also? So proving from scratch that the halting problem is intractable, is that easier? Or reducing a known intractable problem, the halting problem into a given problem to prove that the given problem is intractable? Did you guys do any reduction there? So for instance, to prove that a program is correct, or to prove that 2 programs are equivalent, if you could do that, then the halting problem could be solved by just converting the halting problem into the problem. So I think Sam's answer is the right one. These conversions can be very tricky. Did you guys study, have anybody done algorithms course? Did you guys study NP hard problems? How do you convert NP problem, to prove that a problem is NP hard? You can try to prove it, you have to convert a problem, show that if this problem can be solved, then the SAT problem can be solved also. Okay? So there's an NP complete, you have to show the two-way conversion. So that's the kind of process you have to go through, okay? And if it's obvious, And some of these transformations are not obvious. People have got lots of papers saying, hey, the traveling salesman problem and the SAT problem are both equivalent, okay, for instance. They're both in the NP complete set. So, this is just a judgment call. There was no correct answer there. I just wanted to link this stuff to stuff you guys have studied to just sort of appreciate the broader context. Yeah. Yeah. Yeah, I try to always do that. I feel it's good to go and reinforce concepts you've learned in other courses. Otherwise, you never retain them. And that was good about my PhD exam. I did it in operating systems, compilers, theory, all aspects of theory. So I felt after my PhD exam, I knew as much of computer science as I ever know in my life. Okay, because then you start to become specialized. And so I'm a big believer in that stuff, whereas in our department, we try to specialize you from first semester onwards, which, you get lots of papers. Okay. Now I want to find out the minimum temperature that has been recorded about each city. Okay. So my input is input lines and pairs of city and temperatures. And these readings might be collected from different geographic locations, perhaps. Okay. So what's my reduce function going to be? Minimum, right? So that means, and what will my key be? City. Okay, so this is kind of so mapper ignores position. And now we don't have to choose between key and value. We're getting kind of the key and value from the input. Okay, so we just compute this. We find this out. Reducers convert list input elements with the same key with multiple values to the key with min of values. So we don't have to do sum of values. We can do min of values. Okay. By the way, min is the one problem that both the OpenMP guys and the MapReducer guys address. Okay, the OpenMP guys never address the word count problem. And the MapReduce guys never address the sum problem, and we'll see why. Okay. So the two A's get reduced locally. B goes straight here, B70 and A90 go straight. By the way, I kept vacillating between min and max, so maybe my numbers aren't right. The A60 and A90 go to one reducer. These go here. Out comes A60, out comes B55.
So did we address your partition option for this, or are we just saying that there is a way to move them?
So if you don't give a partitioning function, it just has one. But you can write your own partitioning function.
Wait, what is it?
It's the system.
Your map.
The infrastructure. You wrote the map and reduce functions. There's a lot of infrastructure working behind the scenes, just as in OpenMP. You wrote the directives, but there's a pre-compiler working and there's a runtime system around. So it is the infrastructure.
So on the bit of partitioning, would you be partitioning in two steps here or just one? The mapper, if it tosses to each thread, maybe based on key value, could that thread have a set thing it sends it to for a reducer where you don't have to partition again?
No, you are partitioning here too. You have to use the same criteria for partitioning in both cases. You don't want to find the min between A and B. You want to find the min between the A's.
I'm saying maybe all of your partial reduction A thread has a set place it sends it to, a set reducer. So you only have to partition once before you get there.
You can have only one reducer. So number of reducers is again not under your control, right here. But if you have multiple reducers, they better be in disjoint sets. And just to make life easy, I don't believe there's a separate partitioning function for local and remote. Though you could, in theory, have that too.
Okay.
But they have to be consistent with each other. Okay? It shouldn't be that the other reducer, you have to go and do extra work.
Okay, I see.
And actually the partitioning function can be different, but the reducing function is the same. Okay?
Right.
So you can have only one thread handle everything for this guy. And you can have 5 different reducers remotely. Yeah.
So who's controlling the number of reducers there?
The system,
And
the infrastructure.
So would that,
And you can probably give it some configuration file saying these are the things I would like.
so who is going to be the system? Is it the one who's distributing what goes where?
Everything.
Or-
Whatever you're not doing, the system is doing. You just write the map and you write reduce functions. You saw that. You saw what you wrote. You didn't write the for loop that goes and distributes it. You didn't write anything to create the threads. There's a lot of stuff you didn't do. That's happening here. Right? Yeah. We do sum. Okay, round function. Round, neither MapReduce guys nor OpenMP guys talk about, but we talked about it during OpenMP times. So I want to go and round up all my values. So how will I do this?
So this really depends on the functioning you want to use here.
I mean, how do I want it? I'm not saying depends. Tell me how to do it.
Okay, I mean, the way that I would do it is I would associate them each with a key, and then
So hang on. What's the key now?
so you want to round each of the values,
Right.
and then return a list.
Again, just forget about this last step. Huh? I don't know about this last step.
No last step.
Okay.
Your desired output is that list of values, each of them is rounded.
Yes.
Then you associate them all with a unique key. So
Okay, good. You associate them each with a unique key.
and then your MapReduce function, instead of summing them.
No, there's a map function, there's a reduce function. Tell me which.
Your reduce function, instead of summing them, will do like the sealing operation.
Okay. The reduce function will go and do the sealing, yeah.
do you want to round them all up or just up?
Each one individually. I want just a list of the items later.
Are you rounding them all up or?
It doesn't matter. I mean, that's just a
Okay.
silly
So
question.
let's assume everything is being rounded up, then I would associate each object with a key. It's not going to be unique. Each object's key will be just the integral part of it, and then all the keys with the integral parts will be combined into one, and so.
But I want his scheme goes and gives me the whole list again. I want that list again later of all the rounded numbers. I don't want to go and
The key is the line number, or
yeah. So that's the thing. How do we create the unique key? And he said unique key. He didn't give you the answer how to get the unique key, and you're telling us how to get the unique key.
multiple elements in your line, like
Yeah.
line number,
Okay.
element number.
So now, do we want to do the rounding? So can we do the rounding in the map function also?
You could.
Why not? Why even have a reduce function?
You don't need it.
You don't need it. Because reduce function is necessary when you have multiple values also with one key. This is a very local thing.
You just have to pick which function you're making values.
Yeah,
You
yeah.
could just not have map as well.
Yeah, why were you using the map for this?
I need to go and convert this line number into some key, right? Who's going to do that?
So what I'm saying is like, I'm a bit confused why using a map structure for this is like the option.
Because that's my only option here. I want to go and understand the MapReduce problem.
So assuming we're using MapReduce, how do we do it?
MapReduce, how would you get a unique key?
So like line number is fine. I think.
So who gets the line number, the mapper or the reducer?
So if not model, we would use your mapper. So you
Sorry?
Your mapper.
Okay, so you're agreeing with me.
Yeah, I'm just like, I don't understand why we would use a map problem for this. Like, wouldn't OpenMP do a better job of this?
Why not have?
I have got distributed database, distributed data here. I don't want to put all the numbers in the world into OpenMP, into one process. Okay, and I'm trying to understand my MapReduce problem, okay? The more examples I use, the better I'll understand what the underlying infrastructure is, okay? So let's go and use the thing, mapper converts each position float to position round int. So I did exactly what Andrew was saying, 1.1, 2.1, 3.1, 4.1. And did I not have two things in one line? Yeah, and 4.2. Okay, so I generated the unique keys and I round them up right there. And then I don't need these partial reducers here. I don't want to create these threads. They don't even do anything. So I just send them across, and I don't know whether you can just short circuit them. You can. Okay, so you can just short circuit the reduce process, and out comes your output.
Well, I don't actually know what the partitioning does in that case.
We could write our own partition. Yeah.
Yeah,
Okay.
I actually shouldn't say you can short circuit. I don't actually know what's going on.
But-
I know you can ignore the reducing process. You can tell it not to reduce. I don't
Okay.
actually know what it's doing under the cover.
Okay.
No, you
So that's good. That's good. So that shows us that, reduce can be an optional thing too. Yeah.
You can also use null keys, and the reducer will just be an identity function. It'll just output the values with null keys.
Okay, but I do want in the end the line numbers also with the numbers so they can sort them later and create my original list.
Yeah, you have to do it this way.
I had to do it this way then.
Why did you use floats for like numbers?
Sorry?
Why did you use floats for like numbers?
Did I use floats?
Why did you use?
4.1.
Why did you do 1.1, 2.1, 3.1?
Because there's multiple values in there.
Because there are multiple words on one line.
Why not just make it 4 and 5? Like, why not split
Is-
it into 2 lines?
Because what if you have a line five, so then you
What are we constructing data?
My question is, what if there's more than 10?
Remember, this is being done distributedly. How is the fact that you converted this into a 4 going to correspond to somebody else who got the 4th line?
I see.
What if there's more than 10 values on the line? Well, you started at 4.
No, it can be 1.101. I mean, you can do whatever. Anyway, we use... I'm glad you guys think these are the erudite scholarly questions to ask in this context.
These are probably
You know?
string that's not
I mean-
actually
Yeah,
numbers,
you could make them straight.
because you wouldn't want to deal with rounding
I got
errors.
it.
Okay. So I'm assuming output is or can be sorted by key. And again, that's this outside function we can use later. So another problem we did with OpenMP is first round up all the values and then sum them up. Okay, so we've seen how to do round, we've seen how to do sum. So what happens when you want to compose the two? Okay, so we don't want to assign now individual keys to each value. As in sum, we'll attach, we'll round up the value in the mapper, as we did in the round problem, but we'll attach the key it to a common key, and then we can of course do the sum as we did before and get the final value. Okay.
I have a question.
Yeah.
What happened to the 1.1, 2.1, 3.1?
You don't need it.
You don't need it now.
You don't need to preserve it.
And we don't want
You
it.
don't want the
because
preserving of order.
Okay. Okay, guys. If you can do this problem, you really get it. So in Facebook, apparently this is actually used to find common friends between two users. So we want to find the common friends between A and B, right? A's data can be in some location, B's data can be in another location, and we want to find the common friends. The common friends is going to involve what kind of operation? Two sets we've got. Sorry?
Summing a list of friends.
Subset is
Intersection.
all subsets, yeah.
Intersection.
And I can do the final ones.
My God, you need to shut your laptop too. So it goes and does a intersection, right? It's not going to find all common subsets. That's not needed in this problem. Just because you know how to find all common subsets doesn't mean you use it. Okay? And now that means if A and B, we want to find the common friends, the reducer is going to, so can that be done in the mapper? The subset?
It could be done in the mapper, but isn't it better to
Sorry?
do the reducer?
So the friends are all over the world. And our input is this form. Line 1, key, friends, key is basically, each user's friends is on, let's say, one line. Okay? Yeah.
I know you're trying to explain it, but I don't get it. So I'm looking at line 1. A, arrow, B, C. Does that mean A is friends with B and C?
Yes.
Okay. That's it. I was just not sure
Yeah.
about that.
So can that reduction be done can that be done on the mapping step? The intersection? See what I've got?
I'm confused. What are you intersecting here? I'm not getting it.
What you would try to do find subsets of. So what are we intersecting?
So you have a
And what are we intersecting?
Friends.
We are finding common friends of
different friends.
two users. So you intersect what? If you find the common friends of A and B, what you intersect what?
set of friends.
They're values.
Yeah, can you just, yes. If I've got A and B and I find the common friends, I intersect what? Give me the full sentence you would give in a final exam.
You would intersect all the friends of A and all the friends of B and take the
Intersect, just stop, just stop.
That is the
Okay.
common friends, yeah.
Yeah, right? So can I do that intersection in a mapper?
No.
Because
The mapper just processes one line.
So that you know, this mapper can get my friends, and this mapper can get another friends. Okay. So it has to be done in the reducer. If it's been done in the reducer, the two values you have to intersect must have the same key. So what will be, given A and B, what should be the key, Chris?
You should use the friends as the key, because then when you associate.
Okay. So let me put it again. I'm trying to find the key, the common friends of A and B, right? I'm going to intersect the two friends of A and B. The key should be what?
The person.
Tell me the exact key. I've got
So for
Oh, maybe you combine them together, like AB.
AB. Okay? It has to be AB. Otherwise, they won't go to the same reducer. That's the main idea here. Okay? So what am I going to do in the mapper then? How am I going to process A, B, C?
so the key is BC.
The keys are? So what are the key value pairs I generate?
The keys are A, B, and then C, and then AC.
So what, okay, with the key AB, what do I associate?
C. True.
You're trying to compare A and B.
Actually, you could
There's different. I think there's different ways to do this.
so you could do C because B is implied. Right. You could do C because B is implied. And then with AC you associate B. But if you just add B, there's no harm done. Right?
So you want the key to be A and B, like together.
Together.
So then isn't this set of keys you have like ridiculously large for the friends on the planet?
And why do you think we need MapReduce?
No, I just like, what we'd be talking about is order of like trillion, quadrillion boundaries for number of keys. So I don't really face.
It's n square. And they do it, apparently they do this algorithm every night.
So you're saying Facebook has a quadrillion key map that they manage for this?
Whatever, n square. Whatever n is. I don't know what n is.
Isn't there also a
Wait,
way
it's not, I feel
all
like
your
it's not that hard
keys,
though.
No, but like, is that the best?
where all your keys are the subset of your friends? So
Okay.
like A's keys are B, C, B, and C, where the value is A for each of those.
I'm totally lost here. What problem are you trying to solve? We've derived the solution. Is there a problem you're trying to solve here?
I'm saying
Or you don't understand the solution?
My bit is that this is like a reducer, but the mapper is going to make way more key value pairs than we started with, right?
Sure, n square. That was Chris's problem.
Yeah.
It's a sparse key space also. Most people aren't friends with everyone in the world.
That's true.
Yeah.
Oh, yeah, it's really.
So you know, I'm doing the theoretical approach. This order of n squared is sort of the worst case scenario.
What's our physics anyway?
So, okay. I believe this is the only way to do it with MapReduce. You try to think offline about your solution, okay? But you have to have intersection in the end. And that means that you have to go and, if you're going to do it that way, then you have to go and generate the same key for two friends, and that has to include the two friends.
You will.
Yes.
In my method, but it might be a bit. I don't know if it's wrong, because so A is going to have 3 keys. B.
No, the A doesn't have keys. So what? Okay, you're saying you're taking A, B, C as the input line. You're going to process that how?
B. So BC is 1 key. B is a key, and C is a key. And for all of those, A is one of the values.
So what do I do with the key with what do I do with the key with only one user?
And you reduce it with C's key.
You can't reduce 2 keys
Now,
in MapReduce.
you're reducing the maps.
Why would you generate a key with only one user?
So for line 2, you're going to have.
Okay, tell me what
B
he's getting
as a
at.
key. And A, so
He's not
B has A and has C. And it's
I don't know why we have a key with only one user. I don't want to think any
It's
further.
not going to only have 1 user after the first reduction.
Yeah, you can solve it a piece of rights. Tune me out. Hunter, go.
Okay. I think what Gaddy's getting at is that per person we have a key. So I have friends A, B, and C. I have 3 keys. I have a list after, multiple keys or values for each key of the friends they have. Mapper puts it has one thread per friend.
No, I still don't understand. What am I going to do with the key with only user A?
Create a new pass map of what
You're getting nowhere. I think let's go and let me do it offline, okay? Okay. We'll do this offline, okay? But to me, having a key with only one friend doesn't make sense because you can't take two keys and to do a function on them. As simple as that.
I mean, you can just look at the values behind the keys.
Yes, but what?
And which ones do they share? And then make a new hash.
How do you find the values that they share?
You can't see that if they share the value or not unless the keys are the same.
You can't.
only do operations or do line if the keys are the same.
That's a problem. You can only do a functional operation with the two keys the same. Okay.
So let me get this. Let me repeat. What
Okay. No. I'm going to just show you here in slow motion. Okay. We're going slow here, and I've got only 3 minutes left. Okay. So I'm going to do it a little, different way. So AB, I just put all the friends there. Okay. AC, I put the friends there. CA, I put AB, right? And then I resort CA to AC so that we get the same key. Okay? CB, AB, okay? And I should resort that. I don't know if I do it or not. Oh, I do. Good. So from this, I get BA, ACD. Again, I resort it to AB. BC, ACD, BD, ACD. Okay? So I've got the keys. And now I take the two ACs and combine them into, I find the intersection between AB and BC, which is B, right? And similarly, I find the other values. Okay, the two ABs went there, and AC went, there was only one value, so there's no two values to intersect. So we just output that value directly. ABC, ACB.
So you're also alphabetically sorting the names. So that
I'm assuming that.
yeah.
Just the partition.
Okay. So, like I said, this is apparently what Facebook does according to some Stack Overflow thing I read. That's my reliable information.
Must be.
Okay. But at least we understand MapReduce. We're not trying to understand Facebook here. We're trying to understand MapReduce. Yeah.
So you don't send the BC pair because there's no intersection.
No. I didn't. This is not complete.
Oh.
This is not
So
complete.
you had to send it because if other threads have it, you don't know what goes on.
Yeah, I don't have the splitter for it here. So this took me a long time to make, guys. And even with these two users, so.
So this is finding the common friends of every pair of possible.
So whenever you go and visit some guy's page, you see these are your common friends. That was computed the night before by MapReduce. According to this blog I read. But it makes sense. A good story at least. Okay. Okay, guys, we are out of time and more or less, I'm just going to take 3 minutes more. This is just all text that you can read it on your own. I haven't told you the whole thing, how you configure things. I don't even know how you configure everything. But based on this tutorial I saw, you've got to do a lot of things. You've got to go and run. This shows you how you actually. This is not the concept here. I'm just trying. Since we looked at a real system, I want to just kind of give you a feel for how a real system works. So this is an example of how you might run it. This is how you might build it, compiling and generate. This is how you might create the inputs. This is the map class we saw earlier. This is the remote and local reduce class. You combine these classes into a main class. Okay, so these are just details that you might want to look at just because this is a very relevant system. Okay, and let me just quickly talk about the assignment. Okay, I know at least Chris and Robert have started on it, and we'll talk about that after class. What to do about those of you who don't have time to do it by tomorrow or by Thursday. So what this assignment is doing is trying to give you a flavor for both OpenMP and MapReduce together. Okay, and so it's assuming all input goes to one process, just like OpenMP does. Okay, that goes and then goes to multiple reducers in that process. Okay, that work is split according to the OpenMP way of splitting things by chunks. Okay, and one of these reducers, some of these reducers are bound to slaves. Okay, so they don't have to do the reduction locally. So firstly, you do a bounded buffer based splitting. Okay, so you get experience with bounded buffers, and then you go and send your data to a remote reducer using RMI calls. Okay, and that does partial remote reduction. The other guys do partial local reduction locally. So two of the reducers work locally. One reducer sends its input to a remote guy and gets output back. Okay, then now they start behaving like MapReduce. Now they go and take the partial values and split it among themselves. In the next phase, they run a barrier where they finish the work. Once the barrier, they stop at the barrier, so this gives you practice with barriers also. They go and wait, each one of them gets some keys to do final reduction. Okay, so now we go and do this key-based splitting. Okay, once the things are being split by keys, now they each again have a list of values to go and process. But this is the final reduction. Again, a reducer can go to a remote guy to do that locally. Okay, and so final remote reduction there, and you get the values back. Now the master is executing a join method to go and wait for all these values to arrive. Once the join unblocks, it takes all these values and outputs them out. So you see how you can do barriers, how you can do joins, how you can do splits. So it's a lot of things, but very small things, each one of them. And so this is what the assignment is. Okay, and what's interesting is that it shows you. I've tried to show you the relationship between MapReduce and OpenMP. Here I've shown you that you can take different parts of it and combine them into one. Okay? And this is the output. And here's sort of, I hope this works. Very quickly, the words are this to be summed up, they're added up. So the words go to master. Master goes and creates a bounded buffer of these values. For each thread, it puts a null value there as a terminating key value. So the first thread gets this value, it gets this value again, because the second thread hasn't gotten around to taking a value. It does not do a reduction of these two guys immediately. It's going to wait. The reason it's going to wait is that it's going to collect all this input and see whether it has to send it to a remote guy or not. It doesn't want to send multiple messages to the remote guy. So this way it differs from OpenMP. Okay, A1, the one here, it goes here. And now this guy gets a null value. It says, okay, let me now do my processing. And it goes and starts. And then when it does processes things, it goes and splits the values based on the reducers. So it got the, and the is its own one. So it splits it into its camp. A is the other guy's value. So it puts it into the A's data structure. Because we are splitting by keys now. We've just done the partial reduction. We haven't done the final reduction. Okay, so this is a partial reduction where it got a bunch of key values. Now we want to do the final reduction. So all the the's go to one guy, all the A's go to one guy.
Oh, the partials.
Partial. This is partial.
Oh.
Okay, because we don't know. I mean, there's an A here, there's an A there.
Right.
They have to be combined together.
Okay. Why didn't we show the partial part?
We did. The partial one did not add up. The partial was the two. The two is partial result.
Oh, yeah.
Because there were two the's there.
Yeah.
But we have to go and combine this A1 with that A1. Okay? Yeah.
What's a barrier?
Barrier we saw in OpenMP.
Yeah, is that, okay. I feel like I asked that yesterday too.
Yeah, we just, bunch of threads wait for each other to finish. Okay? Now the second guy says null. It takes its list and sends it to the remote guy. That does its reduction, partial reduction. The results of that are now returned back, and they're split, and it so happens that he gets his own things back. Okay? Now we do the final reduction. Okay? The first slave has only one entry, so he just outputs the two. The second guy gets his input and sends it to the remote guy. The remote guy does this reduction, and sends it back, and the second guy just writes it.
Does this imply that the A from S, the higher one, sends its A value to S, the lower one?
Because that's the way the keys are split.
So it does imply that,
Yeah,
right?
yeah.
So does that higher S go to R, the client, at all?
No. That's what
No, because he's not bound to a client.
So we're saying this is a single client model, so that.
Yeah, I just try to make it easy to program.
So the lower S will communicate with R to do all of its partial
Yes,
reduce?
yes.
Okay, so it does a partial reduce on its values, and then does another partial reduce?
There's a final reduce.
Right, the final reduce, given the values from the other S?
Given the values of other S and given the values assigned to its slave.
And then its final reduce is returned to M, and that's assumed to be the correct reduce at the end.
Yep.
Okay, yeah.
So it's my way of combining things, and it just shows you both aspects together. Okay,
So wait, what was it? The sent to the client.
because the first was this guy's partial reduction list. The second was this guy's final reduction list.
Clients are only associated with one slave.
Yeah. So he's illustrating that some slaves are bound by clients and some aren't. So some are just running locally.
So the from one of the slaves was sent to the client, but
Yeah.
So
The-
where is
what-
that sorting happening?
This is the remote guy is bound to a particular slave.
Yeah.
Whatever is bound to that slave goes to that. So this slave does not. I mean, you understand what? Explain in your own words what reduction is.
What reduction is?
What splitting is. What is the splitting going on? What is the splitting shuffling that goes on in MapReduce?
That's what I'm trying to understand.
You tell me what is your feeling for it? You solved all these problems.
Yeah.
Define it in your own words.
So what I feel is going on here is that
No, what happens in MapReduce?
MapReduce splits a particular input based on certain types of keys and then tries to reduce them for a particular type of function.
Yeah. Somebody want to give a better definition? I mean, this is too vague.
I mean, what MJ said is a lot how I feel, so like, you could say it differently, but I wouldn't change what he said.
Yeah, it does something. That's also true.
The first thing is you go and map all your inputs to the keys and reduce them to some, hopefully smaller set of keys. And then based on some hash of the keys, you redistribute those to new destinations such
And
that
such-
each one has every value for that key. It applies reduction again.
And the two reducers, can they have overlapping set of keys?
Which reduce?
Which reduces.
Any two reducers, can two reducers in the same process or different have overlapping keys?
This is a layering question.
So it's you can't have overlapping keys. So some keys go to some reducers, some keys go to other reducers. So the went to the top reducer. It's not going to go to the slave because that is a top reducer's key, and that key doesn't go to a remote guy.
I see.
And A and An are the bottom guy's keys.
So, reducers for this problem. So R is a reducer, S is not a reducer? 'Cause S is-
R is a remote guy.
I feel like S
Okay.
is using R.
So S reduces,
Yeah.
R reduces.
Yes.
So are
R-
the three of them?
R is remote and S means slave here.
So, yeah, so we use reducer as the term. So after S does reduction, it is a reducer.
S first does partial reduction, then does final reduction.
Yes, so if it does partial reduction, it then becomes a reducer.
It becomes,
Because now it has one key, right? It gave its other values away.
it has its set of keys, which happens to be just one in one.
Right, so to answer your question, I think I understand this clearly now. So if S is associated with the client, it will send the data out to the client after partial reduction for a final reduction.
No, it's not.
Yeah, exactly.
Yeah, it's not.
If S does not have a client, then it's going to do the job of the partial reduction itself for a particular set of
Right.
keys.
And the final reduction.
And the final reduction of some keys is sent to the other reduction based on whether
It's
it's
all
called.
the clients and any slaves that don't have a client are reducers.
Yeah, there's two kind of reducers. There's the OpenMP kind of reducer and the MapReduce reducer. And
That's what I was asking about the layering question here, because it sounds like there's like three segments here. There's master, slave, and client, but some of the slaves are also the reducer.
all slaves are reducers. They're doing both reducers.
I think I know what Chris is asking. So it's like the lower S. It's reducing, but it's really it's using the remote.
It's
guy.
delegating. It's delegating.
Right.
Yeah, delegate.
So Chris's question is, so it's still reducing.
S can.
Yeah. It's no. That's like you ask me a question, and I ask Nirsha to answer it. I'm still answering the question if I say yes. Okay. Okay, guys, and you get the output. So